Okay, so we're back to computational social choice. So I was actually wondering how to organize the class for today, and I decided that the first two sessions will definitely spend on multi-winner elections, or committee elections, or essentially ways of choosing teams rather than particular people. And this presentation is actually based on a tutorial that me and my colleagues Piotr Faliszewski and Nimrod Talmun were giving at a couple of conferences. We actually did, so we prepared these slides together, and we found that this topic of multi-winner elections can be sometimes a bit confusing, but this time I have to actually manage without them, so we'll see how it goes. So this is an overview of the presentation, which I guess you can look at, but we simply start with introduction and preliminaries. So of course, some of the things here we'll go over relatively quickly because they're reminding you of things seen before. And one of them is essentially we're starting from the world of single winner elections. And I want to explain actually why this is so different to choose a team rather than a single winner. So in the single winner elections, we have our set of candidates. They have some preferences. We've seen that they're usually preference orders, there's some voting rule, and eventually we have a single winner. And we're seeking the best, the most widely supported candidate. And this is, of course, impossible, or usually it's impossible, but this is essentially the only tension that we have in single winner elections. So, for example, so essentially, because you can either have someone who is ranked very highly, but by, let's say, majority, but is despised by a large minority of voters. And for example, if you're choosing a president, this is perfectly fine. So consider, I don't know, Donald Trump elections in the United States. Probably a really large minority of the country truly hated him, but it's perfectly fine. For president, this is how we go. It's enough to have the majority that likes you. On the other side of the spectrum, imagine you're using the Doodle website to find a meeting time. Then it's actually, you cannot leave any minority out. You want to find a meeting time that is acceptable for everyone, even if nobody truly likes it. So, so on one point of the spectrum, you have things where you have really wide support for a given candidate, but maybe not everyone really likes the candidate so much. That's a meeting time. On the other side of the spectrum, you have presidential elections. It's better that the majority of the voter likes him a lot, but whatever the minority does doesn't matter. And this is essentially a single-dimensional line of tension that you have between voting rules, and simply choose your position on that line, find the best voting rule for it, that's it. So in some sense, even though it was exciting 3 hours yesterday, in some sense all voting rules or single winner rules are more or less the same, and they're doing similar things, and the world with multi-winner elections is much more exciting, or at least much more complicated. So the basic case of a multi-winner election is, of course, electing a parliament. This was somehow the best way I can draw a Polish parliament. And you can see that suspiciously I didn't draw a circus, but well, anyway. So if you have a multi-winner election and you're choosing people to put in the parliament, then maybe one of your goals should be proportionality. So if there's a certain point of view in the society, then it should be proportionally represented in the parliament. Imagine there are two guys that have very similar views. They're very similar to each other. How many of them should they, if their particular views are not very well represented in the society, then maybe none of them should get into the parliament. But if there's some support for their point of view, then maybe one of them gets in. And if they're widely supported, then maybe both of them get in, and maybe even more people like that. So this is what I mean by proportionality. And this is somehow one of the most intuitive settings for multi-winner elections. But there are more. So imagine, again, a simple business scenario. So imagine you're taking a long flight. Say this flight will take 10 hours. and the airline has to put some movies on the entertainment system of the airplane. And while, of course, in the past we used to say, yeah, and they have limited memory and they can only put several movies, so they have to choose somehow. These days, of course, memory is not a problem, but actually royalty payments are a problem, because to put a movie on a plane, you have to actually pay someone for that. So the airline would like to have relatively few movies, and it would like everyone to be able to watch something, to enjoy at least one movie. So if you have two similar movies, let's say Batman 1 and Batman 2, you only put one of them on the airplane. Because whoever is willing to watch one of them, I mean, he probably would also watch the other, and that's it. So essentially, what we're after in this kind of election is diversity. So essentially, if there are two similar candidates, at most one of them gets in, because he already caters for whoever the other similar candidate would be dealing with. On the other hand, think of yet another situation. So we call it making a shortlist, but it's even better to think of this as a competition. So yesterday we were thinking of Formula One racing as an election, but we can do it in different ways. So again, Eurovision Song Contest is one example where various people provide their preferences, and we're supposed to choose a team or choose the finalists. Or similarly, in terms of making a shortlist, imagine that you're working in a company and you need to hire someone. Or maybe hire a PhD student, even better. So actually, where I did my PhD at the University of Rochester, every year we would get around, I don't know, 300 applications from PhD students all over the world, and we would accept 15. So of course, the first thing was to make a short list of people who we actually really look into more carefully. And in this case, if you have two similar candidates, so let's say two PhD students who seem to have similar CVs, or in terms of Eurovision song, two similar songs, or in terms of whatever other competitions, two people that are doing similarly, then in fact you should either have both of them in or both of them out, because otherwise it seems unfair. Of course, this is subject to some boundary conditions. If it's right on the boundary, then maybe you have to put in one and one out. So these are essentially three completely different settings that have different requirements. So here we had only this one line of tension. Here we already have a multi-dimensional spectrum, and this is what makes it interesting. And in fact, these are somehow the three basic settings, but one can think of many more. We will not really do that in this course, but it is possible, and this is what's happening in research right now. So they're all fundamentally different. Okay, so now the election model will be pretty much the same as before, except we will also look at approval votes. So again, we have election, which is a pair of candidates and voters, set of candidates, voters, like before. And voters are represented through their preferences. In the ordinal model, this is exactly what we've done last time. So the same model, that's it. However, we will also be looking several times at approval model. And this time, as I mentioned last time, we're simply saying, so voter one thinks red is okay, orange is okay, pink is okay. Everyone else is bad for this voter. And here again, pink and green and similar. So on one hand, the ordinal model didn't allow you to express somehow the strength of your preference. So you couldn't just say that you like someone and not others. Here, you can actually do that. You can somehow express strong intensity of preference for an approved set and strong disapproval for the others. But on the other hand, you cannot rank those within the sets. The benefit of of approval preferences is people can actually vote like that. It's much easier to cast preferences in this way. So if you're after political elections, then this is actually a relatively good model. Okay. And now a multi-winner voting rule is very similar to a single winner one, except it outputs a family of size k committees. So a committee is a set of candidates, so now the output is a family of these committees. And again, a few examples at the beginning. In the approval rule, you simply count how many times each candidate was approved. So if we take committee size 2, and then the winning committee is red and green, because the red guy is 1, 2, 3 times approved, the green lady is 1, 2, 3, 4 times approved, and no one else has more. So of course the pink lady has actually 3 approvals as well, just like the red guy, and so is the orange guy. So they're all tied, and we have these several committees. Okay, this is one possibility, a very simple rule. On the other hand, we have something called satisfaction approval voting. You can maybe somehow see it here, but essentially the idea is that in the satisfaction approval voting, so in the approval voting, every voter could give 1 point to everyone he approved. In satisfaction approval voting, you could say, okay, this is a bit unfair. I have 1 point. I can split it over 3 guys if I choose to. So this red guy gets 1/3 from the first voter, 1/4 from the third voter, and 1/3 again from the last voter. The orange guy gets, again, 1/3, 1/4, and here 1/2, and so on and so on. If you sum up these scores, it turns out that blue and green are the winners here. Okay, but of course we can also stay back with the ordinal preferences. You can use border like before and simply take guys with the highest sums of scores. So in this case, it will be red and green. Or you can use STV. And STV, this is actually used in practice, as I told you. In a multi-winner setting, it's similar to how it behaves in the single winner one, but with some complications. So now it's actually getting a little complicated, because candidates ranked with first a given quota times. So a quota is number of voters divided by the committee size plus 1 plus 1. So essentially, if you take if you take K to be 1, the single winner setting, you have n over 2 plus 1. So this means exactly the smallest amount to get a majority. If you take K equal 2, then this will be n over 3 plus 1 vote. So this somehow ensures that you will never have problems of that maybe you have still too many votes left, and it works. So the way this works, in our case, we have committee of size 2. The quota is, we have 6 voters. 6 over 3 is 2 plus 1, it's 3 votes. So you need 3 votes to get into the parliament. So STV is usually used for parliaments, so that's why I'm saying that. So, but to get into a committee, you need 3 votes. So in our election, the red guy is 2 times first, the pink lady is 2 times first, and then blue and orange, which means we have to remove someone who is not ranked first. So again, green lady goes. Then we're removing orange guy because we decided to break ties this way. And now the red guy has 3 votes, which means we're saying that these 3 votes are being represented by the red guy, and he's chosen there. And we have to continue the process. So now the pink lady has 2 votes and blue guy has 1. So we have to remove the blue guy. Oh, actually, we have to remove the red guy because he was already elected. Now we have to remove the blue guy, and now the pink lady, she's the last standing person, and she's also representing the other voters. So somehow we're managing to find representation for this election.
Excuse me, what's
sure.
N small?
N small is the number of voters.
Okay.
So that's, I would say, it's the typical. So I hope I will explain these things, but just so you know. So N is always the number of voters. M is the number of candidates. And we typically take K to be committee size. Committee size. So these are somehow the standard notations used.
So when we pick the red guy,
Uh-huh.
then voters V5, V6, and V1 sort of eliminated, or?
Yes, yes, exactly. Exactly. When there was a moment when we chose the red guy, there were 3 voters, because that's the quota number. So exactly this number of voters was assigned to the red guy, and they're no longer participating in the election. If we had 4 guys that were voting for the red guy, then we would still choose 3 of them, because that's the quota number. 1 of them would be still left in the game. So, of course, this is a matter of tie-breaking somehow, which one would be left. And then, of course, the red guy is also eliminated from the game, and we're only left in this area. Okay. Okay, these were just few examples of multi-winner rules. I hope everything is fine. And yeah.
So, why do we need to remove somebody? So now in this system, each vote counts just once.
Yes.
But it doesn't need to be so. So we just determined that red guy qualifies, and then we continue without removing these votes. And we see that someone else qualifies and so on.
We could, but this is not how the system works.
Okay.
Yes. There are also settings when, so this is a relatively complicated, actually STV is an extremely complicated rule if you actually want to describe it precisely. And there's really many of implementations in the world, and many of them are studied. This is a relatively simple variant, but there's, for example, a variant where we assume that voters can be fractional. And simply, initially every voter comes with weight of 1. But for example, if we had 4 supporters of the red guy, but the quota value would be 3, then we wouldn't just remove 3 guys and leave 1 of the supporters in. We would simply decrease their weight so that altogether the total weight decrease was 3, and we would have somehow fractional voters that would only contribute with this weight. Okay, we're actually we'll be back to STV probably in a long time from now. We'll occasionally see it in passing, but these are just examples. And now, what are we after in this talk is, well, you can barely see that. There are some applications like this: shortlisting, jobs, awards, competitions, movie selection, parliamentary elections, and so on. It's good for storytelling, but it's not very good for mathematics. So we decided we somehow distilled from this 3 idealized goals. One is called individual excellence, and this was the case of shortlisting, so similar candidates should be treated identically. Diversity, similar candidates, at most 1 gets in, because we want a diverse set of guys in. And proportionality, where similar candidates get in depending on how much support they have. So this is somehow, this is what we distilled from observing what multi-winner rules can be good for. And we'll be looking at axiomatic properties of rules. So somehow we want to match axioms with our idealized goals. And of course, we have various algorithms for computing the rules. So actually on algorithms, we will mostly focus in the diversity section, but we still have some in the middle. And there's lots of rules, lots of properties, and lots of various things that appear here. And we'll try to explain all the ideas that are on this slide. Okay. So our first goal is individual excellence. And so we will have actually 3 sections of this kind: nature of the committees. This is the first one. Actually, there will be some interlude in the middle, but that'll come. So, okay. I was told that apparently 11:15 is relatively early in Petersburg. So just to make sure, in case everyone is awake, and we're getting on to the real business now. So actually, in this talk, there will be, I guess, I'm wondering, maybe there will be a bit fewer proofs, but certainly more pictures. Okay, but anyway, we're doing excellence. And the idea, so what we're after is, we're given a group. We have some preferences of judges, voters. We need to select the K finalists. So we're selecting a group, and we're selecting K finalists out of them. And we somehow expect that later on, one of them will be chosen as a winner. However, we see this as completely different tasks. So in particular, so if this was choosing people, for example, to invite for interviews, if you're hiring someone, then this choice would be made, say, based on their CVs, and we're getting people to come. But the final selection would actually be made, they actually come to the place, they talk, they discuss, and then we vote. So it's essentially, the assumption is that the final selection is based on completely different preferences than the shortlisting process, which means that we're not thinking about that there will be some single winner at the end. We're simply focusing and choosing the best case guys, and that's it. Okay, now I told you the intuition is that two similar candidates, either both are selected or both are rejected. Okay, that's intuition. We would like to somehow, I can't say we're going to make it formal, but I want to at least make it somehow visual. Because you can, if you try to, actually, okay, let's try to make some discussion. So we want a voting rule where two similar candidates, either both are selected or both are rejected. So we've seen several voting rules. So we've seen plurality. That was yesterday. And in the multi-winner setting, it's called SNTV, single non-transferable vote. And this simply means we're choosing whoever gets most votes. We can imagine K-Borda. So we have these linear scores, and we're choosing the guys with highest scores. Today, we have seen approval voting. So this means everyone approves of some guys, and we're choosing whoever is approved most frequently, K of them. We have seen STV, and there are several other rules, but let's say we have these four. 1, 2, 3, 4. Now let's do a voting. We are supposed to, we want a rule that will choose similar candidates. Who thinks plurality would be a good choice? Okay, who thinks K-Borda would be a good choice? 3. Who thinks approval voting? Who thinks okay, do you approval voting? Okay, STV? Okay. So I somehow have a feeling this vote did not add up to the number of people in the classroom, but okay. So now how can we actually verify this intuition? What can you do? I mean, you can try some election. What does it tell you? So we actually thought of way of the following system. We'll have a two-dimensional domain experiment. So here is a big cloud of points. I think there's about 2,000 points there. So there's a Gaussian distribution here with 250 points. 250. Okay. I have to go back a bit. So there are two kinds of points on this picture. There are light gray points. These are candidates. There are dark gray points. These are voters. You probably cannot tell one from the other. But that doesn't matter because they're all distributed in the same way. So essentially, it's a big cloud of, okay. So you have 250 voters and 250 candidates that are distributed on from a Gaussian, two-dimensional Gaussian distribution here, the same here, the same here, and the same here, okay? Now, every point who is a voter forms his preferences by computing the distance to every candidate guy and simply sorting them in the increasing order. So the closer a guy is, the more he likes them. But since we're looking at approval voting, in this case, rather than simply approving, having an ordinal vote, for each voter, we're simply, again, choosing from a Gaussian distribution with mean of 10 and standard deviation of 10, the number of closest guys he approves of. So in this case, if you take a voter, he approves on the average about 10 guys next to him, and usually a bit more. I mean, okay, not usually because it's average, but actually, indeed it is usually because with standard deviation of 10, the number would often go below 0. So when it goes below 0, he just approves the closest person. Okay, and this is so. First of all, is the setup? Is this clear? So you look like you're doubting. So should I explain again? Okay. So let's see. I guess this part is still visible. Okay. So what we have is a two-dimensional space. So actually, the space is not two-dimensional. I mean, it's two-dimensional for two reasons. First of all, two-dimensional pictures are somehow nice. Second, it's actually, in political science, people often believe that you can explain preferences this way. So you can say that, for example, one direction is personal freedom. It's personal freedom. The other axis, let's say, is economic freedom. So depending where you are on the spectrum, you will have your worldview somehow described. So maybe if you value highly personal freedom and economic freedom, you're very much libertarian. If somehow your economic freedom is you value it less, it means okay, I want the country to be protective. I want social system to be helpful for the people. And again, if you want more personal freedom, I guess you want more liberty. If you want less personal freedom, you put more on tradition. Now, if let's say there are some candidates, like candidate C1, C2, C3, the position of each candidate is his somehow ideal position in the spectrum of possibilities. And if we have a voter, then he has some distance to each of these candidates. And I guess I'll move this guy a bit closer so that I can, okay, like this. So he's certainly closest to C1, then to C3, and then to C2. So voter V would have preference order C1, C3, C2, okay? So on the other hand, we could also say, but how do we form approval preferences? In a similar way, let's say if these were approval preferences, and we would say he approves two closest guys, then he would simply approve C1 and C3. And so in this experiment, for every point, in this case, we choose the number of closest approved guys to be on the average 10, but from the standard deviation of. Okay, so we also have committee members, and they're marked in red. And if we choose a committee of size 1, this is just this one red guy. It's a bit strange, because if you think about it, maybe if you're after individual excellence, then maybe you should be in the center. And this is a bit unintuitive, but the reason why you would like to be in the center is that we were saying that two similar candidates should be treated the same way. And this means this somehow should be symmetric. The whole distribution was symmetric. So if we focus here, then it's a bit strange. But okay, we chose this guy, and we're increasing the committee size. Doesn't look so well. So we somehow are close to the centers of the Gaussians. Not exactly there, but this is more or less what we get. So in this case, approval voting, not so nice. Satisfaction approval voting, this weighting of things, does not seem to help much. Okay, not happy. One approval, which is the plurality or SNTV, yeah, not great. Not great at all. You can see how this looks like completely random noise, which is not so unexpected given its random data, but still. There's a rule called block, which is actually quite amusing. This rule, this is actually worth discussing a bit. I don't need to write. Actually, I do. In this rule, so the reason why this rule is interesting is that it's actually used in a lot of kind of simple elections or local elections. So usually, when you would say, if someone told you, we're going to vote and we need to select a group of I don't know, 3 people, what would you do? Probably, and most people do that, say, okay, each of us puts 3 names on a piece of paper. The names that are mentioned most frequently, they are the winners, right? It's pretty intuitive. So this is what the block rule does. We can assume that that everyone has a preference order, like this. And if we're looking for committee of size k equal to 2, then the top 2 preferences each get a point, and whoever has most points wins. Okay, it seems like a relatively natural way to elect a committee. And this is also, for example, I think in France, there was a university who was choosing PhD students. using exactly this way, that every professor would vote like that. So now, when we choose, this is committee of size 1. Committee of size 3, strange, it changed. This guy is no longer in the committee. Oops, changing more, moving. Exciting, exciting. Keeps moving. So if we go back, and if we look at each of these previous ones, they were only adding winners. But here, when we're looking at block, it actually, as you increase the committee, it can actually remove someone from the committee. And this is a really nasty feature when you think of this in terms of, say, hiring committee or contests. So here, imagine that you're applying for a PhD student position, and we're choosing committee of size 1. So then we're looking at top preferences only. So the red guy wants to become a PhD student, and he gets a letter. Congratulations, we only had one position, and you were selected. And a week later, he gets another letter. Actually, we had 2 positions, and that means you're no longer good enough, because the green lady gets 3 points and the pink lady gets 3. So this is a particularly unpleasant situation for the excellence, individual excellence setting. People still use this rule, and this can happen in practice. It does not happen so frequently, mostly because people don't change the committee size during the election. But it is somehow a flaw of that system. Okay, now one of you voted STV. This is what we get. So this is actually quite nice. It is completely irrelevant for the sake of choosing an excellent committee, but you can see that this actually very nicely spreads over the whole spectrum, which means that apparently STV will be quite a good choice if we're choosing a parliament or if we're choosing a proportional committee. So not here, but it's actually a very good rule on its own anyway. Okay, and finally, most of you chose K-Borda, and you can congratulate yourself because this is what it does. Yes, so we really got exactly the center. So the similar guys are in, similar guys are out, and only on the border there's some trouble. Okay? So all the previous ones are not great for excellence, but Borda is. Okay? But in fact, I was cheating at least a bit. So whoever also thought approval was a good choice can actually be right. Because this is again approval election, but instead of choosing this approval set to be the closest guys to me from the Gaussian distribution, now for each candidate I choose uniformly at random the number of people he approves of. And this of course gives exactly the same result as K-Borda. The reason why it gives exactly the same outcome is that it's pretty much the same rule. Because if you think about it, if every voter chooses the number of approved guys uniformly at random, then more or less the score that the candidate gets is actually proportional to the support he would get under K-Borda. So in fact, for approval rules, it's not only the rule that matters, but the distribution is somehow much, much more important on the number of approvals. Okay. Yeah.
I chose approval voting because it's not intuitively what is similar candidates in case of K-Borda. What are similar candidates?
That's a good point.
Gets similar points, but they are not similar.
Right.
Different people vote for them.
That's okay.
Should we treat it as similar?
That's actually a very good point. And this is exactly why we are looking at this two-dimensional model, because here the notion of two similar candidates is actually clear. So if candidates are light gray, so they're barely visible. So let's use dark gray. If we have a point here and a point here, then we could say they are similar because they have similar in this spectrum of opinions. They have similar points of view. So in fact, if we computed the preference orders, they would always be close to each other in the preference order. So indeed, you're right that in in basic K-Borda, it's possible to have two candidates with nearly the same score, but one will be supported by, for example, one half of the voters and the other by second half. And you could say that they're exactly as opposite from each other as possible, and yet they have similar scores. So indeed, in this case, you're right. So we can essentially, one of the reasons why we're using this two-dimensional view of preferences is exactly because we can use such intuitions as two similar candidates. Because here it makes sense. On general preferences, it may be undefined. So it's a good point. And of course, not every election can be represented in this two-dimensional space. This should be quite clear. So for example, the only guys that can be ranked last are on the outskirts, and the guys in the middle, they're never ranked last. They're usually actually ranked somewhere in the middle. Okay? So that was the intuition. So we saw that K-Borda is a nice rule. Now we often want to actually somehow express axiomatically our preferences. So one axiom that we thought was good is committee monotonicity, which is exactly, if you have a committee of size K and you increase the committee size, no one gets kicked out, we just add a new person. And a different axiom is Gerlain stability, and I will explain that in a moment. And we would hope that if we can satisfy both these axioms, then we somehow have a perfect rule. But let's first focus on committee monotonicity. So the way it works is, in fact, every committee monotone rule generates a ranking of candidates. So if we have a profile and we choose a committee of size 1, a committee monotone rule gives us some committee, okay? Committee of size 2 can only add. Committee of size 3, add, and so on. And of course, the order in which they were added means that we have a ranking. So, and in fact, in the world of single winner elections, this is exactly the notion of it's a social welfare function. So a social welfare function produces a ranking of candidates from best to worst, and we can simply we can make a multi-winner rule out of simply choosing top guys. So every committee monotone rule corresponds to a social welfare function. So essentially every single winner rule, well, not block because we saw it doesn't work, but every single winner rule that somehow can be used to produce a ranking gives us a good rule for excellence. And this also means that this choice of excellence is somehow similar to the choice of president, or to the single winner setting. Okay, so the next property is called Gerlain stability. And we're saying a committee is stable if there is no selected candidate, such that a majority of voters prefers some non-selected one to him. Okay, definitions are nice, examples are nicer. So let's look at an example of what we mean. So we thought that K-Borda is a good rule. So here we have a K-Borda election. If we compute scores, we get scores for the candidates. And of course, the red and the blue are the winners. So now we're asking, is this committee stable? So we can, for example, we can ask, is it the case that the pink lady is actually better than blue and she has a right to replace him in the committee? In this case, we would say no, because the blue guy is better than the pink lady in 3 votes, and she is better in 3 votes, which means that there's never a majority for removing her from the committee. Okay, so we say, okay, this is fine. However, if we look at the pink lady against the red guy, oh, well, red guy is first in 2 votes, but she is better in 4. Which means that according to Gerlain stability, she's fully entitled to remove the red guy from the committee and come in her place. But now the red guy is annoyed, and he says, I should be in the committee because I'm better than the blue guy. And indeed, in 4 votes, red is ahead of blue. So blue is removed, he comes back. And but if we simply used K-Borda committee, we would not succeed. So we would actually, majorities would be against some of the candidates. So Gerlain stability claims that this cannot be the case. So that we couldn't be, there would be no majority that can actually object to some member of the committee being elected. Okay? So how can we satisfy? Yeah?
Can there be a cycle in such case?
I would think yes, certainly, because essentially it's like just like with the Condorcet winner, and if we have preferences that are cyclic.
But, I mean, in Condorcet winners there is a tie.
Yeah, exactly.
We get rid of even of tie.
Just a moment. If we have preferences like this,
Okay.
so if we somehow say A should be in the committee, but then B says A should be in the committee, so actually C says, okay, but I'm better than A in 2 votes. So we move to C. But now B says I'm better than C in 2 votes. So we move to B. And now A says I'm better than B in 2 votes. So we move to A. So we have a full cycle. And of course we could do it with the larger committee. Okay. So you can see that this Gerle instability is actually very close to the notion of a Condorcet winner. So why don't we try to use K-Copeland rule, which is Condorcet consistent, and which proceeds as follows. We draw this majority graph. So here, so for these preferences, if you can see, they're somehow special, because the red guy is always better than orange. So red better than orange. Whereas this is actually a Condorcet cycle. It's just like the ABC there. So red is better than orange, then they are tied with everyone else because we have equal number of voters, and we have this Condorcet cycle here. And if we say we give 1 point for a victory and half a point for a tie, then this guy gets 1 plus half, it's 2.5, and so on. So now this would be a Gerle unstable committee of size 2, because there is no one that can actually attack this committee. However, Copeland would choose one of these, which is a bit of a problem. And luckily, and in fact, this is a general property. Every somehow trivial extension of Condorcet will somehow fail Gerle instability. I will show that in just a second. But there is a simpler, there is another very related rule which simply says, be like Copeland, except you only get scores from outside the committee. So you get let's say 1 point for a tie in this case, but outside of the committee. So red guy here has 1, 2, 3 points. Orange has 1, 2, 3. We're getting 6 points. And this is a winning committee. If you looked at this committee, then here the pink lady gets only 1, 2, 3. And this guy he gets nothing, 1, 2. So gets 5 points. This is how this rule works, except it's NP complete. So this very minor change made it NP complete.
Sorry, I missed. What is 3 plus 3?
Okay, so the way you compute the score of a committee, so in Copeland, you would compute each score individually for each guy. So simply whoever he defeats, also within the committee. Under the NED rule, it's a number of external defeats. The score of this committee can be only computed jointly. So the score of red and orange is that red contributes 3 points, because here each tie is equal 1, and orange contributes 3 points. So they get 3 plus 3. But in this case, pink contributes 1, 2, 3, and the blue contributes 1 and 2. He doesn't contribute this because it's within the committee, and he doesn't contribute this because he's losing. So in this case, really the Gerle unstable committee had won.
And gray edges indicate what?
A tie. So like the orange guy is, in 3 votes he's ahead of these guys, and in 3 votes he's behind. Okay? The problem is that as soon as you require this Gerle instability, the rule becomes NP complete. And there's actually a bigger problem. So, of course, maybe you're convinced that this Gerle instability is a nice concept. I hope you are. At least it's somewhat nice. The problem is it's completely incompatible with committee monotonicity. So we had these two basic conditions, and you cannot have both of them, because this is a Gerlain stable committee of size 2. This is Gerlain stable committee of size 3. And that's it. You simply, when you increase size, you cannot just add something to this committee to maintain stability. Okay? So we named two nice axioms, and you cannot have both of them. In fact, Barbera and Collio somehow they finished there, but when we picked up this topic, we decided it's actually an exercise in futility, because this notion of Gerlain stability is a bit silly. It's enough that, so Gerlain stability says that a committee is stable if there's no selected candidate, such that a majority of voters preferred some non-selected one to him. Now we say Gerlain, a strong variant, a committee is stable if every member of the committee is preferred by a strong majority to every non-member. So Gerlain said simply that it's enough that no one attacks you. Well, in the strong stability, we're saying it's not enough that no one attacks you. You have to attack everyone. So if somehow they were defeating everyone outside of committee, this would have been a strong Gerlain stable committee. And there's plenty of strong rules. So for example, a variant of K-Copeland, which is polynomial time, a variant of Maximin, which we didn't talk about. And a lot of these, there's some NP completeness, but there's also approximation. So things become actually possible. So probably this Copeland rule is one of the better choices. But somehow it's not clear why. And so somehow, actually, I want to say something else. So K-Borda and K-Copeland are very different rules. Copeland satisfies both our axioms, K-Borda only one, but somehow it feels that we have a wrong axiom, because if you actually compare Borda and K-Copeland and you start increasing their committees, yeah, not much changes. So it seems like there is something deeper that makes these rules behave similarly on these profiles. So, okay, now you see some difference, yeah? Very important. So, committee monotonicity on its own is not, it seems it's not sufficient to capture individual excellence. For example, SNTV is committee monotone, although I will get back to that. Gerlain stability is maybe too focused on Condorcet-like notions. So we feel that there's still some need for some better axiom, some better capture of what this individual excellence really means. But so far we don't have it. Okay. So I hope you're still alive, you're still not asleep. I wouldn't dare saying still active. And we're moving to interlude, which is committee scoring rules. So here we will, so today's, at least this multi-winner course has quite a strong social choice component, but we'll also see some actual computer science here. And first, we need to give a definition of a committee scoring rule, and this is relatively important. So a moment of focus is needed. So a single winner scoring rule is something, as we have seen last time, you associate a score with every position in the vote. Now, if you're a candidate, this was Borda scores, this was approval score. If you're a candidate, your score is simply sum of the scores. So here you get 1 plus 0 plus 0 plus 0 plus 0 plus 1, 2 points. Okay? Now we want to generalize this notion to committees. So imagine you have a preference order, again, red, orange, pink, blue, green, and you have a committee of red, pink, and blue. Okay? Now, we're saying that this committee has position 1, 3, 4, because this guy's position is 1, her position is 3, his position is 4. So now the position of a committee is actually a sorted vector of the positions of the members of the committee. Okay? And now we assume we have a function that gets this sorted vector and outputs the score of the committee. And this is a committee scoring rule. So there's a huge difference compared when you compare it to a single winner setting, because in the single winner setting, if you had m candidates, so let's say you had 10 candidates, then it was enough to give 10 numbers, the scores for each position, to specify the voting rule. Now, if you have 10 candidates, but committee of size 2, then you need 10 times 10, or 10 times 9, I guess, numbers to specify the rule. So in principle, if you have m candidates and committee size k, you need m to the power of k numbers to specify the voting rule. And this grows exponentially. So you cannot usually just express these things explicitly. You need some formulas to express rules like that. Okay? So I hope this is clear. And now we have some examples of committee scoring rules. So the first 3 things you have seen already, the next 2 are new. So again, let's, SNTV is the plurality. It uses scoring function, which simply says, I approve of the first, if these are positions of the committee members, I'm giving approval 1 score to the first, to the highest ranked candidate. I could also actually write that so I could also write that the scoring function is I1 through IK is equal to approval score 1 of I1 plus approval score 1 of I2 plus so on approval score of 1 of IK. Why can I make such a summation? Because this is approval 1 score, which means I'm giving 1 point if the position is 1 and that's it. So the top guy in the committee maybe is ranked first. But certainly the second best guy in the committee will not be ranked on the first position. He can be at best ranked on the second position, and so this will always be 0. And this will be always 0. So that's why in this definition we have actual just one element of the sum. But this is, if you have, like in the k-border, if you have actual sum of the same kind of functions, then this is just like using a single winner scoring function. So in this case, red and pink are winners. So for k-border, this is clear, right? So much fewer of you are speaking today. So I need, again, some verbal confirmation that this is clear.
Could you define what alpha, beta,
Sure. Yes, so this was actually quickly done here. So this is border score, which is m minus I. M is the number of candidates minus the position of the candidate. A T approval score is alpha T of I. So T is the number of approved guys. So this is 1 if I is smaller or equal to T, and this is 0 otherwise. Okay? Okay, so are we better now? Or is it okay? I mean, because, you know, if you don't ask questions, I will just go on teaching and I can go straight to, I don't know, middle of nowhere. And okay, but for k-border, we're simply summing up border scores. That's easy enough. For block, again, this was the rule where I told you that if we have committee size 2, then for top 2 positions, you get a point, and otherwise you don't. So in this case, the green lady has 4, and there's a tie with 2. Now,
so when we take f of the committee, it says like this committee has sort of number, like.
Yeah. So again, going back to the. So for every vote, we compute the position of the committee, and it's a sorted vector. So maybe it would be important to make a. to draw another example. So imagine we will have.
It's not the final order, it's just final, it's order of one voter.
Yeah. So that's what. So if you have, say, A, B, C, D, this is voter 1. You have voter 2 with B, D, A, C, and you have voter 3 with C, A, D, B. And let's say you have committee. Okay, choose your committee. 2 guys. Someone,
AC.
AC. Okay, A and C. So we would say that position from voter 1 of committee SAC, he is 1 and 3. So this is a vector 1, 3. Now, if we take voter 2, the position is, well, it's 3 and 4. But if we take voter 3, the position is so here it used to be AC, but here it's CA. But still, C is the first guy in this vote, so its position is 1, 2. So we're taking the positions of the guys and we're just sorting them. This is it, okay? And now when we have these positions, then the score of the committee, which actually I somehow didn't say, but it's good that you asked. So we will have the score for position 1, 3 plus the score for position 3, 4 plus the score for position 1, 2. And this is the result of committee AC. And you choose the committee that has highest score. Okay? Yep.
Are we still thinking about shortlisting?
No. So so we had shortlisting up to now. Now we have we're introducing a class of committee scoring rules, and they're actually good for many things. So we will actually want to see, we'll somehow want to match axiomatic properties of committee scoring rules to various applications, and we'll try to see which of them are good for shortlisting, which are good for diversity, which are good for other things. Okay. Okay, so I hope that the first 3, the SNTV, Borda, and block are clear. Are they? So if it's unclear for someone, then I want this person to stand up and jump. Hey, it's clear to everyone. Very good. This is called manipulation. Okay, but this actually really is important. So, okay, so the next rule, so block is also polynomial time, easy. And in fact, these 3 rules, because since they have sums of the same type of function, they're actually polynomial time computable. The next rule, Chamberlain-Courant, and essentially the whole diversity section is focused on this rule. So I think I will keep on defining it like 3 times to make sure you understand it correctly at various points of time. But the way this rule works is that if we have a committee, in this case, red and green, and we're saying that the score of the committee is simply the Borda score of the highest ranked member of the committee. So for this particular committee, we can say that in vote V1 goes to red guy because he's better than green, so we get 4 points from the first voter. From the second voter, we get 3 points because here green is better than red, and she's at the position of 3, so this is the same here. And eventually in vote 6, red is better than green, so we get the 4 points. Okay? So this is definition of the rule. And finally, another definition of the rule, another rule is called proportional approval voting. And here we're using K approval as the score. So we also were using K approval in block. The difference is that you get full K approval score for your top ranked committee, but only half of this score for the next one, 1/3 for the next one, and it decreases somehow harmonically. Okay, so if we have committee size 3, So if this was a vote, and we had committee red, orange, and blue, we would take 1 full score for the red guy, but only half for the orange, and only 1/3 of 0 for the blue guy. Okay, this is an example of a rule. This rule is actually very important, but we'll get back to it in quite a while from now.
Why does it make sense? Is it some
Why?
moving?
Okay, why does it make sense? The answer is, for some reason, this harmonic sequence makes the rule proportional. And we'll try to explain it a bit at the very end of the course. But intuitively speaking, this is actually related to don't apportion method. So you could say that when you, so imagine this process, so here we're simply maximizing the score. But imagine that this is an iterative process, that you just choose first one candidate, then second, and so on. So at first, you choose one candidate that gets highest approval score. So you just find a candidate that has highest approval score, and you put him into the committee. Now, when you add another candidate, everyone who already has this guy somehow is only worth 1/2. So okay, let's make it even more simplistic. Let's say that we have voters, some v1 through vn prime, and v prime 1 through v some. Okay, it will be complicated. Okay, we have just 2 groups of voters, where here everyone votes like A, B, C, A, B, C, but here everyone votes X, Y, Z, X, Y, Z, and so on. So essentially these are groups that have, let's say, opposite preferences. So if you elect a candidate for the first group, if you somehow choose A into the committee, they already have one guy. Let's say that there is also the number of these guys, let's say it's 2t. The number of these guys is t. Okay, so there's twice as many of ABC guys than XYZ guys. So when you choose your first committee member, he has 2t points because 2t voters put him there. So he is elected. But now the value of these guys is decreased by half. So now this is only 1/2. So now their value is only t. The value of these guys is only t. So we either put in B or X. If we put B, then these guys already have 2, and they're worth only 1/3 now. So the next we put in X. So we put in X. So you see that if we had this 2t, and we're choosing 3 committee members, we got exactly proportional result. So this is somehow intuitive answer. There's a formal proof why this works, but that's probably the best I can do in the short amount of
Do
time.
you mean that this proportional voting is good for proportionality, yes?
Yes, yes.
And Chamberlain current is not good because in this example what we have?
Yeah, exactly. Actually, in this example, Chamberlain Courant would choose A, and everyone here would be satisfied. Then it would choose X, and everyone would be satisfied here. And then it would do some random thing, because already everyone is satisfied. So if you, for example, if you had one more voter who had preferred
3t, then again we choose AX if we choose 2, yes?
Yeah, but if we had one more voter with WUV, then Chamberlain Courant would choose A, X, and W to make them all satisfied. So we're actually jumping ahead because we will be explaining these things, but okay. Okay, so these are how these rules are defined. And the whole family, before we describe the whole family, actually this whole class of community scoring rules is quite interesting on its own because it has some nice features. One of them is consistency, which says that if we have one election where red and green is winning, and we have another election where red and green is winning, if we put these two elections together, then lo and behold, red and green are winning. Does this seem normal to you? Yeah, it's pretty normal. I mean, they were winning here, they were winning there. Committee scoring rules are essentially the only multi-winner rules that have this property. In fact, this is also true in the single winner setting. If you have two elections with the same winner, if you put them together, they will have the same winner only if it's a single winner scoring rule, with just a few other axiomatic requirements, such as neutrality and anonymity, which are basic things that say every candidate and every voter is treated the same. So the proof of this, so this is a nice slide. See, it's moving and it's colorful. To prove this statement, it takes 30 pages of mathematics, including topology, graph theory, algebra, basis of various things. So when my co-author is not here, I call it 30 pages of pain. When he's here, I say it's very nice proof. It is, I don't have a reference for it here. I think it's axiomatic characterization of committee scoring rules. It's available on arXiv. It is probably the most complicated paper I was ever involved in terms of mathematics, just to do this.
So what are restricting on this electing rule?
So you're asking for the specific result?
Yeah.
So the specific result is as follows. The rule has to be neutral, which means that every candidate is treated in the same way. So if you permute the set of candidates, the set of winners gets permuted the same way. The rule has to be anonymous, which means the order of the voters is irrelevant. Okay, that's quite straightforward as well. The rule has to satisfy this consistency, which is somehow the most important feature. And the rule has to have what's sometimes called Archimedean property, which means if you have one election with a given committee where a given committee is winning, and you have another election where a different committee is winning, so if you take them together and you clone one of them sufficient number of times, then eventually the winners of the cloned one win. So essentially, these are somehow, so neutrality and anonymity say this is a basic requirement for a fair rule. Consistency is this kind of defining feature. And this Archimedean property is also kind of obvious because it says if you have strong enough majority, you can get your way. So these are really minimal requirements, and yet only committee scoring rules satisfy this property. There's one other technical caveat about the model of elections, because in our proof we're somehow using slightly more complicated output. So we're not only giving which committee is winning, but actually for each pair of committees we can say which one is better. Okay?
So what I don't understand is what doesn't qualify? What is the
We had a formal definition of committee scoring rule.
Yes.
Okay.
Yeah.
So the formal definition is exactly this. This is this process that so when you have a vote, then you have for a committee you compute the positions. You have a scoring function. There's only there's one basic requirement on the scoring function, which is in fact reflected in the axioms. So I mean the functions you're adding here for the voters anyway. But the only requirement is that if you have committee position I, which is I1 through IK, if you have committee position J, which is J1 through JK, and if it so happens that you always have, actually, sorry, the other way around, smaller or equal here. So if essentially every position in I is at least as good as position in J, then we require that the score associated with position I is greater or equal than the score with position J. So this is just basic monotonicity. And a committee scoring rule is defined by a function that satisfies these properties and which computes a score in this way. That's it. That's a full formal definition. And of of course, so a rule is a committee scoring rule if it can be expressed by such a function. Okay? And we are guaranteed to have consistency, and it's quite obvious to see that that consistency holds, because if this committee had highest score in this election, and it had highest score in this election, then when we add them, in a committee scoring rule, you add their scores. So it's still the highest plus the highest still has to be highest. The fact that these are the only rules that actually satisfy the axiom, plus the kind of the basic axioms around it, is actually, it's very difficult mathematics. So for single winner setting, it was proved in the 70s, I think, by Peyton Young. And their proof is actually just essentially the base of induction for us. But it's somehow much more involved in the multi-winner setting. Okay. Another property that is satisfied by all committee scoring rules is candidate monotonicity. So remember that we had committee monotonicity. Now candidate monotonicity is slightly different. It says that if we have some committee, so if we're focusing on a single vote, if we have some committee and say if we improve the position of the green lady, then the green lady will still be in the winning committee, but maybe another one, not the one that she was in before. And this is also a general property of committee scoring rules. Okay. Unfortunately, this is another general property of committee scoring rules is that it's always possible to find an election where a given committee is winning. But aside from these three, and the fact that the committee scoring rule defines a rule perfectly up to affine transformations, these are more or less the only joint committee properties of all committee scoring rules, which is also why we decided to partition this class into subsets. So we have class of all committee scoring rules, and all the rules that can be expressed as a sum of the same functions, we call them weakly separable. If this function does not depend on k, then we call this simply separable. So k-border and SNTV are separable, block is only weakly separable. Okay? If the function depends only on the position of the top guy, like in SNTV and in Chamberlain Courant, then we call them representation focused. If the rule is somehow only using approval k, then we call them top k counting. It's a bit of a silly subclass, but it was introduced for technical reasons. If the rule is a sum of functions weighted by some coefficient, so here it's 1, half, 1/3, and so on. Here it's 1, 0, 0, 0. Here's 1, 1, 1, 1, 1. Then they're called OWA based, because OWA is a so-called ordered weighted average operator. And so we are interested in these subclasses. And now, 15 minutes before the end of the first lecture, you will actually see computer science. Because it's computer science club. But I guess you knew what you were doing when you invited me, or I hope so. So the problem, now the funny thing is that polynomial time computability is essentially only within the weakly separable class. So things like k-border. And there are some strange rules that somehow sneak out on the, even beyond OWA based. And aside from that, almost everything is NP complete. And in fact, if you take k-border rule, so let's introduce a rule which I will call k-1 best. I don't need this. Okay, we have a rule which I call k-1 best, and this will be, so for the position function f1 through fi1 through fik, this will be just like k-border. Actually, I will use for now let's say like border, I1 plus I2 plus border of I k-1. So this is the same like, if I use something exactly the same like k-border, except I stop on the second to last guy and not on the last guy, this rule becomes NP-complete. Even such a minor difference makes it NP-complete. And here I will give you the proof. Actually, I will give you a proof for a slightly different rule because it's much easier to give such a proof, and then you will have to believe me it translates.
What is NP-complete? Is finding as such a set, best set?
NP-completeness is for decision problems. So you have to ask a question, is it?
Is there a set?
Yes.
Four or more? Or
Exactly. This is the problem. Okay, so this k-1 best rule will work as follows. So imagine we have, we somehow, now these guys are voters and the candidates are movies. So green lady, I told you I will confuse colors, thinks that Batman is worst, but Superman is best, then Bond, then Shrek, then Woody Allen. Okay, so this is just a different representation of their preference orders. So if we take committee of Superman and Woody Allen and Bond, then they're marked here. And so the green lady just takes value from her all but one most valuable committees members. So she gets 7, the orange guy gets 7 as well, the red guy gets 1 plus 4, 5, and here 2 plus 3, 5. Okay, so this is how the rule would work in the Borda setting. But we will actually use an approval setting. Okay, so I will. Here what I'm doing, it's a bit of a jump, but instead of using Borda here, I'm using approval scores, and also I'm allowing approval preferences because the proof is much easier then. And you will see that this actually makes the proof much easier. The reduction is from the vertex cover problem. So as I told you yesterday, in vertex cover, we are given some graph, we're given some number, and we're asking, is it possible to choose k vertices so that every edge is touching some chosen vertex? So here, for example, if I choose V2, V5, and V4, then I have a perfect vertex cover. Okay? I can express this as I can give names to the edges, and I can express my, so here I call it utility function, but this is essentially this value I'm associating with each candidate. So my candidates are the vertices. So by the way, it's always a mess when you discuss elections and graphs in the same place, because an election is E equals V, E equals CV, so E and V are used, and a graph could be V and E, so it's always a problem. So what we usually do is we say that an election is a pair CV, and a graph consists of set of vertices of G and set of edges of G. It's still not perfect solution, but at least it works. Okay. So in other words, I will be using a rule that sums up the approval scores of all the committee members, except for the one with the lowest approval score, if there happens to be one. Okay. So I'm saying, so I will now say that my voter, every edge is a voter who votes exactly for the vertices that he touches. So edge E1 is touching V1 and V2, and he's approving V1 and V2. Okay? Now I'm adding new voters, somehow complements of the edges. So for E1, I have G1 who approves exactly the opposite of what E1 approves. So this is why I say that we jumped from the ordinal to the approval setting, because in the ordinal setting, each of them would have to approve the same number of guys, but it's easier this way. And now, let's say my committee is V2, V5, and V4, which is a correct vertex cover. And now, the score from the first pair has to be 3, which is the size of the cover, because here we have 1, 0, 0. We drop 1, 0, so the score from the first guy is 1. The score from the second guy is 1, 1, and we drop the lowest value, 0. So altogether we have 3. And this is true for each of them, right? Yes? No? Yes. Okay. So if we set the utility, so or the value that we want to achieve is k times the number of edges, which is kind of half the number of voters, but fine, then we have such a committee only if there was a true vertex cover. On the other hand, if we take a vertex cover, or if we take a set of vertices that was not covering everyone, then an uncovered edge will not give you these k points, or 3 points in this case. So here, the top guy, the edge is not approving anyone from the committee. So you drop the lowest score, but you still have 2 zeros, and that's it. But the bottom guy, he has 3 points, but you have to drop the lowest one, which is one of the ones, so you only get 2. So even though all the other are happy, you actually get less. So essentially, if the committee corresponds to a vertex cover, you get the full score, and if the committee does not correspond to a vertex cover, you get a little less. Okay? And the same works for this Borda-based variant, but the proof is much longer. You have to play with a lot of nonsense, so I didn't want to put this on the slide. Okay, is the proof clear? Okay, very good. So we will, I guess we still have a few minutes, so we will actually jump back to the shortlisting. So we said that committee monotonicity is a nice feature for shortlisting, and committee monotonicity means that if you increase the committee size, then the committee increases by 1. So if the only rules within the class of committee scoring rules that are committee monotone are exactly separable rules. So their function is a sum that doesn't depend on the value of k, sum of the same function. It's also a relatively complicated proof to show this. On the other,
this is a separable rules, and what we are claiming those are?
We're saying that within the class of committee scoring rules, the only rules that have the committee monotonicity property are separable rules. This is a formal theorem that it's much easier to show that this consistency, but it's still not so completely trivial. And so they are committee monotone. On the other hand, we also have something called non-crossing monotonicity. So I told you about candidate monotonicity, where if I improve somebody's position, he's still a winner, but maybe the whole committee changes. So here, in non-crossing monotonicity, I'm saying that for example, if I push this orange guy, and he improves his position, but he doesn't pass any other committee member, then the committee is still winning. And in fact, this property is exactly satisfied by weakly separable rules. So non-crossing monotonicity and committee monotonicity are essentially characterizing things that are happening in this area. And I'm claiming that these axioms are actually exactly what are kind of very nice for the shortlisting tasks. So committee monotonicity, committee monotonicity, we have already agreed on that. Non-crossing monotonicity is quite intuitive as well, because it means that if you have a team of strong guys and one of them improves without hurting anyone else from the team, then clearly the whole team got stronger. So it still should be winning. And that was all nice until we realized that both K-Borda, which gives this nice concentrated result, and SNTV, they both satisfy these axioms because they're both separable. This was a bit of a disappointment, except that actually it was not, because we were reading a newspaper, and a random newspaper article actually convinced us that both of these rules are very good for shortlisting. I wonder, you probably cannot guess what this newspaper was about, so I'll have to tell you. The article was, it was in the times of ski jumping competition, and this was a 4-hill tournament, and the article actually said, and we want to find the best 10 ski jumpers of all time. Now, okay, every World Cup competition in ski jumping gives you a ranking of candidates. That's just like an election. If you collect all of them, then you get a set of ranking, you have a full election. And what the journalist did was simply he looked at how many times a given ski jumper had won a World Cup thing. So essentially what he used was exactly SNTV. And this was a very reasonable way. This way, because he simply realized very good ski jumpers tend to win competitions. The more you won, the better you are. He completely ignored second places, third places, and so on. It probably wouldn't change much. But still, the experiments had shown here that SNTV sucks. But the axioms actually said it's good for this shortlisting. And indeed, there was an application where it was. Which means that actually there's always some tension between theory and experiments and practice. So essentially one cannot get blinded by these pictures. There's some evidence of good quality, but not always. Okay, so we'll get on with diversity after the break. There will be more computer science there, I promise. There will be actual algorithms.